Have to finish up the sequences chapter real quick, and again, before we dealt with arithmetic sequences, which means you had a common difference. We were always adding or subtracting something to get to the next number in the sequence, to get to the next term in the sequence. This time we're going to deal with geometric sequences, so it's slightly different in terms of how you get from one term to another. So again, just a reminder, arithmetic sequences, they have a common difference, meaning they're linear. Alright, if I want to get from term 1 to term 2, I may have to add or subtract a 7, or add or subtract a 9. Okay? And again, these are linear. Always going to be linear. Now, geometric sequences, on the other hand, are slightly different. For a geometric sequence, that's called a common ratio. A common ratio. Okay, remember, a ratio is just a comparison of one number over another. Typically it's a fraction, and these are not going to be linear, because again, if we have a common ratio, that means we're multiplying to get to the next number. So 2 times 4 is 8, 8 times 4 is 32, 32 times 4 is 128. Okay, as we go through that, it's getting larger and larger and larger, and as you see from that example, that this is not linear, this is actually exponential. So geometric sequences are going to be exponential. As a reminder, if you guys don't remember the common form for an exponential function, that's going to be y equals a times b to the x, where a is your starting value, b is then your growth or decay rate. So again, this is the form that we're going to be dealing with for the next however long it takes us to get through these notes. All right. So example number 1. Determine the explicit and recursive formula for the sequence 7, 21, 63, 189. So just like in arithmetic sequences, we are going to have explicit and recursive. So remember, recursive is going to take the form of y equals a times b to the x. Explicit is going to take that form. Recursive, on the other hand, is not going to be that. It's going to be some number that you used beforehand multiplied by something else. Okay, so let's do explicit first, and then we'll get down to how to build the recursive. So again, we're going to have y equals a times b to the x. That's what our explicit is going to be. Now, 7, 21, 63, 189. We have to find the common ratio, or the growth rate in this case. All right, so if I'm looking 7, 21, 63, 189, that's easy. Times 3, times 3, times 3. So our b in this case is 3. Now we need our a. Now our a is the starting rate, or the starting point. Sorry, the starting point. But remember, this is the first term. This is the second term. This is the third term. This is the fourth term. I am not going to plug in 7 for a. I'm not starting at 7. Remember, the starting point for any function is going to be the y-intercept. Okay? So we actually have to work backwards. So if I'm multiplying by 3, that means I have to divide by 3 to work backwards. If I take 7 divided by 3, I just get 7/3, right? So my function is y equals 7/3 times 3 to the x. And again, if you wanted to figure out what the 15th term or the 16th term was, you would just plug in 15 or 16 for x and crank that out. All right. Now, recursive, on the other hand, isn't that easy. It is really easy, but it's not that type of function. It's not going to be y equals a times b to the x. Now, remember, with recursive, you have to use the term prior to get the current term. So with arithmetic sequences, it was mainly a of n equals a of n minus 1 plus or minus some number. All right, that's how recursive looked for arithmetic sequences. Recursive for geometric sequences is basically the same thing. It's going to be a of n, and if you want to call x n, you can. If you see this as n, guys, it's the same thing. But a of n equals, well, 7 times 3 is 21. 21 times 3 is 63. 63 times 3 is 189. So again, if I'm going to create what I just had, all right, I'm going to basically multiply my previous term times 3. I mean, that's it. That's all we're doing. We're taking the previous term and we're multiplying it by 3. So 7 times 3 is 21. Then plug 21 in. 21 times 3 is 63. Then plug 63 in. 63 times 3 is 189. 189 times 3 is so on and so forth. You guys get what I'm saying? So again, just like how arithmetic was a of n minus 1 plus or minus some number, same concept here. It's going to be a of n minus 1 multiplied by some number. That's how it's always going to look. If you want to put the 3 in front, you can, but I'm going to put it on the side just because why not? Second example, create the explicit and recursive formula for the sequence 40, 20, 10, 5. Now, if you're looking at this, you're probably like, oh, Mr. Z, this is easy. We're just dividing by 2, right? I mean, we are, essentially. But with these exponential functions, guys, remember, it's a growth or decay rate. We're not dividing by anything. So if you see division, all right, if you see 40 divided by 2, or 20 divided by 2, or 10 divided by 2, you have to put it in terms of multiplication. So if we're dividing by 2, all right, what else could we do to get the same result? So what could we multiply 40 by to get to 20? What could you multiply 20 by to get to 10? What could you multiply 10 by to get to 5? Your answer? 1/2. So my growth rate, well actually in this case it's a decay rate because we're decreasing, my decay rate is 1/2. An easy way to figure out what the common ratio is, guys, is to, in this case, is to take, well, 20 divided by 40. Take two terms next to each other and divide them. That's 1/2. Alright, take 5 divided by 10. That's 1/2. If you did it up here, you could have taken 21 divided by 7 and got 3. Like, you can get the growth, you can get the common ratio very easily like that. So if you're stuck, just take the previous number and multiply and divide it. Okay? So recursive. Well, actually, we're not done with explicit. Our starting value. If we're dividing by 2 or multiplying by 1/2 to get to the next number, that means we have to, well, work backwards. 40 times 2, that's going to be 80. So my starting value is 80. That means y equals my starting value times my decay rate raised to the x. Recursive, same concept. I take my previous value, or my previous term, and what do I do with it? I'm multiplying by 1/2. I'm taking 40, multiplying by 1/2 to get to 20. I'm taking 20, multiplying by 1/2 to get to 10. I'm taking 10, multiplying by 1/2 to get to 5. So again, guys, recursive, explicit, both are, I mean, semi-easy to create. Again, recursive, it's not that easy to use, or it's not that efficient to use, I should say, because, again, you have to know the previous term to be able to use it. So if you wanted the 20th term, I'd have to know the 19th term, which means I'd have to know the 18th term, which means I have to know the 17th term, and that just gets annoying. So again, in my point of view, guys, explicit is the way to go if you ever need to figure out a term in a sequence, but here's how you create both anyways. That's all we're doing with these, guys. So if you want to, actually, I suggest pausing and trying the next 4 examples on your own, because that's what they're there for. All right? So again, go through each example, and basically try them on your own. If you want to check your answers after, you can fast forward to the video and look at all my answers at the end and see if you're right. You don't have to watch the entire thing. Otherwise, best of luck to you. I'm going to go on and do the rest of them for you in case you guys are curious how they're done, because some of them may look semi-difficult. All right, but let's move on. Number 1. 5, 20, 83, 20. So again, we're trying to figure out the explicit and recursive for both. Well, if I'm looking at this, that's times 4, times 4, times 4. I mean, I could do 20 divided by 5 and still get, 4. So I know that my B value, my growth rate is 4. Now remember, this is the first term, second term, third term, fourth term. I need the beginning term. I need the y-intercept. I need that starting point. So if I'm multiplying by 4, to work backwards, I divide by 4. 5 divided by 4 is, I mean, if you want to call it 1.25, sure, but it's actually 5/4. So my function is my starting value times my growth rate raised to the x power. My recursive formula remember, this number right here, you're going to multiply by whatever your growth or decay rate is, and it's 4. And that is, or those are your two functions. Number 2. Notice how number 2 is slightly different. To get from 4 to -8, now we're switching signs. So you have to put that negative in there as well. 4 times 2 is 8, so 4 times -2 is -8. -8 times -2 is +16. +16 times -2 is -32. So notice, guys, when you're switching signs, that means your growth or decay rate is going to be negative. Okay? So that means my B value is -2. My A value, well, let me work backwards. If I divide by -2, my starting value is also -2. Because again, 4 divided by -2 is -2. That's my starting value. So y equals -2 times -2 raised to the x power or the n power or whatever power you want to call it. The recursive, again, is just a sub n equals a sub n minus 1 times -2. Number 3. 162 to 108 to 72 to 48. This may look somewhat different. It's definitely not as crystal clear as the previous ones were. So this is where you have to take your terms and divide them. So actually take 108 and divide it by 162. So if I take 108 and I divide it by 162, I get 0.666666, which is also considered to be 2/3, guys. So my growth rate is 2/3. My growth rate is 2/3. Now, my growth rate is 2/3. That means I'm multiplying by 2/3 to get to each number. I mean, if you take 108 and you multiply that by 2/3, you get 72. All right. If you take 72 and you multiply that by 2/3, you get 48. So again, your growth rate is 2/3. Now we need to figure out the starting value. So if we're multiplying by 2/3 to get to each one, that means we're dividing by 2/3. You have to work backwards. All right, and you know that if we're dividing by 2/3 to work backwards, we don't divide by fractions. Okay, instead of dividing by fractions, you have to multiply by the reciprocal. So I'm actually going to take 162 and multiply it by the reciprocal, which is 3/2 or 1.5, and I'm going to get my starting value, which is 243. So again, if I'm working backwards, I'm dividing by 2/3, but you guys know if we divide by 2/3, you have to multiply by the reciprocal instead. So my multiply by 3/2, my starting value is 243, my decay rate is 2/3, or my common ratio is 2/3, raised to the x power. Now, if we're going to do our actual recursive, a of n equals a of n minus 1 multiplied by our common ratio, which is 2/3. We take one term, multiply it by 2/3 to get to the next. Finally, guys, last one, number 4, and then we're done. 98 to 14 to 2 to 2/7. So obviously you can kind of figure out what you're getting at, but if we take 14 and we divide it by 98, we're going to realize that our common ratio should be 1/7. Sorry, 1/7. So if I take 14 and I divide it by 98, I'm going to get 0.14287, yada, yada, yada. Regardless, it's 1/7. Okay? It's 1/7. So if it's 1/7, we have to work backwards. That's times 1/7. That's times 1/7. That's times 1/7. That means if I'm working backwards, I have to multiply by 7 to get my starting value. 98 times 7 is going to be 686. So again, my zeroth term is 686. So y equals 686 multiplied by our growth rate, or it's in this case decay rate, 1/7 raised to the x power. Our recursive formula is just the previous term multiplied by our common ratio, which is 1/7, and you're done. Again, guys, geometric and arithmetic sequences aren't that bad. They're quite easy. As long as you understand how to create both types of formulas, whether it's explicit or recursive. So hopefully you understood that. It's a quick lesson. There's no backside because, again, there's nothing else we can really do with geometric sequences. So once you guys are done with this, you got some practice problems to crank through. So best of luck. And if you guys have questions, be sure to ask me for help. Otherwise, take it easy.